Selamat pagi, Ibu, Bapak, dan rekan-rekan yang saya hormati. Salam sehat untuk kita semua. Perkenalkanlah, nama saya Wira Endratami, Sekretaris dari ASHRAE Indonesia Chapter. Selamat datang kembali di acara ASHRAE Indonesia Chapter Webinar Series. Pada kesempatan hari ini, ASHRAE Indonesia Chapter Webinar Series kembali hadir dan membahas topik yang sangat penting dan menarik bagi kita semua, khususnya bagi para pemilik dan pengelola gedung, teknisi dan engineer, konsultan, dan semua pelaku industri gedung dan bangunan, yaitu indoor air quality, energy conservation, commissioning, sustainability, resilience, and other good stuff. Sudah hadir di tengah-tengah kita dua narasumber yang sudah sangat expert di bidangnya, yaitu ASHRAE Distinguished Lecturer Mr. Jim Newman dan Regional Application Consultant Belimo Automation Malaysia Mr. Alvin Chan. Saya ingin menyambut juga moderator yang akan memimpin acara diskusi kita, yaitu Bapak Ardiansyah Yatim. Beliau adalah Research dan Promotion Chair di ASHRAE Indonesia Chapter. Sebelum kita masuk ke sesi selanjutnya, saya ingin menginformasikan dan mengajak seluruh peserta webinar untuk aktif berdiskusi dengan menyampaikan pertanyaan atau berdiskusi kepada kedua narasumber hari ini dengan memanfaatkan fitur Q&A. Dan nanti tim digital kami yang akan memberikan format untuk kita semua supaya kita bisa menuliskan pertanyaan kita masing-masing. Dan juga selain itu akan ada sesi polling atau survei yang akan kami lakukan. Saya ingin mengajak kita semua untuk aktif mengisi polling atau survei tersebut, karena hasil dari polling tersebut bisa menjadi acuan bagi para narasumber dalam menyampaikan materi presentasi mereka. Baiklah, rekan-rekan, untuk mempersingkat waktu, mari kita sama-sama masuk ke sesi diskusi panel kita yang akan dibawakan oleh moderator kita pada hari ini, yaitu Bapak Ardiansyah Yatim. Pak Ardi, untuk waktu dan tempat kami persilahkan. Terima kasih.
Terima kasih, Bu Wira. Selamat pagi. Tes suara saya terdengar jelas? Apakah suara saya terdengar?
Kecil, Pak.
Oh gitu. Bagaimana sekarang? Masih terlalu kecil?
Udah mending tapi masih agak kecil. Mungkin bisa di.
Oke. Sebentar saya coba keraskan. Sementara saya ganti nanti pada saat presentasi. Baik, terima kasih ASHRAE Indonesia Chapter. Terima kasih juga untuk seluruh pengurus research CTTC ya, Pak Asep, kemudian tim panitia, dan juga tentu saja kepada pendukung kita, sponsor dari Belimo, juga kepada Bapak dan Ibu hadirin yang sudah bergabung pada pagi hari ini. Perkenalkan, saya Ardiansyah. Saat ini tadi sudah disampaikan oleh Bu Wira, adalah Research Promotion Committee Chair di ASHRAE Indonesia Chapter. Hari ini benar-benar menarik topiknya, di mana kita akan kedatangan dua speaker. Pertama adalah Jim Newman. Jadi nanti kita akan coba membagi menjadi 3 sesi, di mana Jim akan bicara pada 2 sesi pertama, ya. Dan kemudian di sela sesi tersebut akan ada kesempatan untuk bertanya langsung. Tapi tidak perlu menunggu sampai waktu bertanya, Bapak, Ibu bisa menuliskan di chat. Nanti kita akan coba mungkin summarize atau gabungkan kalau ada pertanyaan yang sama supaya lebih efektif. Sesi ketiga oleh Mr. Alvin Chan dari Belimo juga akan membawakan materi dan akan ada sesi question and answer. Baik, Jim, are you there?
Yes, I am. I just had to unmute myself. I wanted to keep everything quiet while you folks were talking.
Sorry, first I will try to introduce you with Bahasa Indonesia, because most of the audience are, I think, fellow Indonesians, although this one is open for international participants. Jadi Bapak dan Ibu yang saya hormati, Jim Newman merupakan ASHRAE Distinguished Lecturer DL ya sejak 2010 dan tahun lalu menjadi ASHRAE Fellow, satu tingkatan status yang paling tinggi di ASHRAE ya sebagai Fellow seperti itu ya. Di Indonesia baru satu nih Pak John Budi, mudah-mudahan kita bisa menambah lagi nantinya. Beliau adalah penulis di position dokumen tentang energi pada tahun 2008 di ASHRAE dan juga merupakan past vice chair dari TC di Technical Committee tentang Industrial Air Conditioning dan juga beberapa TC lainnya. Ya. Kemudian beliau juga menulis sebagai anggota TC tentang climate change di Handbook ASHRAE 2021 Fundamentals. Silakan cek nanti di handbooknya ya. Kalau sebagai anggota kita berhak mendapatkan satu kopi dari handbook tersebut ya. Jim sudah banyak berbagi tentang topik-topik green and sustainable di media massa, di radio, TV, kemudian juga memberikan seminar di seluruh dunia sehingga kita sangat beruntung bisa mendapatkan kesempatan ini hari ini ya. Mudah-mudahan bisa kita optimalkan. Kemudian dia juga sudah publikasi di Building Operating Management Magazine tentang sustainability dan resilience terhadap perubahan iklim. Nanti juga akan diberikan linknya. Salah satu artikel terbit baru kemarin di bulan September 2021. Baik, saya rasa langsung ke Jim. Nanti saya akan coba menggunakan bahasa Indonesia dan bahasa Inggris. Mohon dimaklumi kalau nanti ada yang terselip gitu tertinggal, baik ya. Jim, thank you very much for attending, for coming in, and then for your availability to share your knowledge, your experience on today's webinar. So I would like to give the floor to you. You can start the presentations, and then we will have a question and answer after the first sessions and after the second sessions.
Very good.
Yeah, the floor is yours. Go ahead.
Okay, thank you very much. I just put this slide up so you can see some of the organizations in which I am heavily involved. Sometimes it's too many organizations. I don't get enough work done, but that's the way it goes. So here's what we're going to discuss today. I'll give you a little bit about my background, and then we're going to get into all of these things. Now, this presentation is not a technical presentation. This is a presentation to perhaps introduce you to some new ideas and other ways that you can make yourselves be more useful to your owners and your facility managers and your building engineers and other people that you deal with to help you make more money and help them do a better job in what they're doing. So what we're going to do is we're going to have some poll questions, which is going to be put up by the IAC chapter, and that will help me know a little bit better who actually is on this call, so I can kind of orient the call to what most of you will be looking for. Okay, so we're going to have 6 questions. They're going to, and when you see these poll questions, they're all very simple to answer. They should be very quick to read them and to answer them. So we'll give you about a minute to do that, and just slide your whatever, whether it's your finger or your the mouse or whatever, just down the questions, and just answer each question one at a time. Okay. So if we could get those up.
You haven't shared your presentation yet?
Oh, can you not see my presentation?
No, not yet.
Oh, there's the problem. Okay, just a second. Let me get out of this. And that's what I didn't do, was share the screen.
Yeah.
Okay. So now let's go back. Can you see it now? Whoops.
Not yet.
No? Oh boy. I just shared the screen, so I should have been on. Let's try it again.
Yep. Okay, it's open.
Okay, now we go.
Yeah. Could you please put it on the presentation? Great.
Okay.
Okay.
Okay,
Now
I'm
we-
sorry about that.
No
This is what
problem.
we're going to be talking about. Like I said, it's not a technical presentation. It's for you to figure out what you can do to be of better use to your clients. And here's some of the organizations that I'm involved in, obviously very heavily in ASHRAE and some of these other organizations, U.S. Green Building Council, the Building Owners and Managers Association, which is exactly what it says, building owners and facility managers. So for an ASHRAE engineer, it's a good organization to belong to, as are some of these other ones. So here's what we're going to discuss. Like I said before, only now you can see it, I hope. And
That's clear.
again, it's not going to be technical. It is going to be, it's for you. And we're going to have these 6 poll questions, which we should be able to put up. Do I have to take mine off for you to put the poll questions up or not?
I think it's good. The committee will show the polling now. Now it's showing.
Okay, there we go. So these questions are going to go relatively quickly. It's like I said, to let me know who's actually on the call. And the way you work this is just take your mouse or your finger or whatever and go down and you'll get all 6 questions.
Jadi Ibu Bapak silakan mengerjakan pollingnya. Ini untuk survei awal. Jim tadi ingin mengetahui profil peserta sehingga nanti delivery-nya akan disesuaikan dengan majority-nya. Silakan diisikan. Jim, I just
Can you make this a little larger?
Okay. I think they can do it by themselves. There's like a box on the right top corner if you want to expand it.
Okay, I'll let people who can't read it. I mean, I can see it fine, but it might be good for others to do it. So if most of them are yes and no, except for I think the first one. Yeah.
Ya, silakan Bapak Ibu diisi pollingnya. Setelah itu disubmit hanya 6 pertanyaan. I'm just explaining to them to give their polling submission on it.
Sure,
Jim.
sure. I actually caught a few of the words that were said before.
Oh, really? That's great. Yeah. We do hope that you can come to Indonesia anytime after this
That would be nice.
pandemic. Yeah.
Well, we'll see when it really ends, if it ever really ends.
So we're gonna give a couple of minutes before we have the polling results displayed. Pak Ferdian, Pak Komite will maybe just 1 or 2 minutes more. Right, Jim?
Yeah, I think so.
Okay, great.
I mean, you're looking at the answers. I can't. So are most of them getting to number 5 and number 6?
Well, I did, but let's wait for the committee to show.
Yeah, but
now.
you've seen it before.
Silakan Bapak Ibu diisi sesuai dengan apa masing-masing ini ya pandangannya.
Okay, I'm also going to try and talk a little bit slower to make it easier to understand. That's what I had to do in Madrid, Spain, when I spoke to the regional conference. It's like, okay, we know you can speak slower, so just do it.
Thank you for that considerations. Yeah. So, Pak Teren, do we have the polling ready?
Think we're about ready?
Let's see. Yeah, I think we can display the result. The computer can help with that. Okay. Wow. Jim, can you see the result?
Okay, got it.
Yeah. A lot of engineers coming today. And then wow,
Okay,
we have
so it's
interesting.
1/3 ASHRAE members and 2/3 not. Okay.
Yeah.
So some of you who are engineers, you need to join ASHRAE.
Right. Yeah, that's true. So we have around 30 more new members then if today they are registered.
Okay, go down a little bit further on that number 2, so I can see. Did anybody fill out anything else besides architect, building owner, contractor, engineer?
There are like 15% answering other.
Okay. Okay, why don't we go down a little bit?
Well, you can scroll the polling tab on that.
Oh, I can do that myself?
Yeah,
Oh.
yeah. I think everybody able to see the polling.
Oh, yeah,
There's
okay.
a poll button at the bottom. And then you can scroll to see the answers.
Okay, about even for energy audits. Oh, very even for IAQ legal cases. That's so you
Yeah,
have
that's
you have a lot of
surprising.
litigation in Indonesia.
Well, that's surprising. Maybe
Yeah, I figured that there's more litigation in the United States than anywhere else, but almost 50% is amazing. Okay, building energy analysis, good. PQ, that's kind of figured on that. Now, how many people are actually? Oh, okay.
140, almost 150 participants.
Okay. All right, good, excellent. All right, thank you very much. So the next slide, for those of you who, oh, I got it. It says I'm screen sharing. Huh?
Yeah, your presentation is showing. It's perfect.
That's strange. Okay. For those who are in ASHRAE or think they're going to be in ASHRAE, one of the things we find is that when we become active, if you can talk about something to somebody else or train somebody else, you really know it. The other thing that we do in Detroit, Michigan, we have a lot of meetings with other organizations. So you're meeting other people, like if you're an ASHRAE member, you're meeting building owners or facility managers or other people like that when you go to the meetings, and it's a social setting. It's not like you're trying to convince them to buy something from you or to do something with you. It's social. So it works out very nicely. So here's what I would like you to think about as we go through this presentation. depending on who you are, you know, the building owner says to the architect, build me a building and here's what I want in it. And eventually the architect gives the mechanical and electrical engineers his half-done drawings and said, okay, put in the equipment. And that's what the designers do. And then the maintenance people hopefully keep it running properly, the maintenance personnel and the building operators. But what I want you to think about as we go through this is, who are you? How will I, as the whatever you are, influence all these other people so we can keep indoor environmental quality and energy consumption relatively balanced? Here's something that is very big today because change is happening faster and faster. It says here, the winners will be the rethinkers, not the retrenchers. If you keep on doing what you've been doing, you're going to lose ground very, very quickly in what's going on today. It's not just climate change, it's everything else. So let's get into it here. In the United States, buildings use 65 to 70% of the energy, and 30% of it is wasted. 30% on the average is wasted. This is actually very amazing. So why do you have to be so concerned about HVAC systems? Because it's the heart and lungs of the building. And you shouldn't let people compromise. Now, what happens when a building is being built and the cost starts going way over the budget? What happens? Well, what happens is people start doing what's called value engineering. And value engineering usually means taking money out of the HVAC system. They're not going to take it out of the good looking, the prettiness of the building, like if they've got Italian marble or these other things that are very, very expensive that make the building look good. That's not where they take the money out. They take it out where it's easy, the HVAC system. So we're going to look at some of that. So what happens to HVAC systems as time goes on? Well, here's what happens. Green goes to gray very, very quickly. And what we've designed as design engineers, those of us who are design engineers, often doesn't go in properly, or it doesn't get taken care of. And here's something that Bill Harrison, who was a president of society several years back, and this is really based on a study. Most buildings will lose up to 30% of their efficiency in the first 3 years of operation. The first 3 years, they're going to lose 30%. So let's look at something that building owners need to know. And those of you who are trying to design better buildings and are getting some resistance, is know that the cost of construction of a building is only 5% of the overall cost of ownership over, say, 10 years or 15 years or 20 years, whatever it is, because you've got all these other things that go into the cost of the building. There's taxes, there's insurance, there's utility costs, and the biggest cost of the building is the people. The people are far and away the largest cost of the building. So if you have a good HVAC system that's efficient, that's quiet, that gives people a good indoor air quality, they are going to be more productive. So let's look at the way we used to design buildings. 40 years ago, like I said before, a building owner would go to an architect and say, here's what I want. I want to pay so much money for it. And that's what I want. And they'd go back and forth a couple of times. And typically the architect would start designing it. And about halfway through, he'd either give it to an engineer or engineers, mechanical, electrical, etc., who weren't in the firm, or if it's an architectural engineering firm, they'd throw it over to somebody on the other side and say, okay, here it is. And we've done jobs where they don't leave enough room for the mechanical rooms. They don't leave enough room for the ductwork, and on and on and on. And I used to call on a very famous architect who headed up a big architectural engineering firm, and his mechanical people were always complaining, how are we supposed to do this? We have no room for anything. I said, well, let's figure it out. That's when I was more in sales than in consulting. But today what we're using is integrated design. The architect and the engineering firm and the owner and the facility managers, if it's a large firm, all get together. And when we do a LEED project, LEED certified by US Green Building Council, we want everybody at that meeting. In fact, if it's a larger company, large organization, and has facility engineers in their buildings, I tell them we're not gonna do this pre-design meeting until you can tell me everybody's gonna be in this meeting, because we're gonna make some decisions in this meeting, and the people who run your buildings know what decisions should be made better than you do and better than I do when I'm talking to a building owner, for instance. Now, that's today, integrated design. Tomorrow, we have to look at what's really happening today. Can we use design parameters on temperature and humidity that are from 30 years ago or even 20 years ago? The way things are going with climate change, when we're having 100-year floods every 10 years or things like that, and there's more drought around the world. At the same time, we're having more floods in other parts of the world, and the temperature's going up. We're not getting as cool at night. It's higher humidity. So we're looking at these things like sustainability and resilience. And as you heard in my introduction, I wrote an article on that you'll have a link at the end of the presentation where you can read it. And we're looking at net zero. Are we going to get to net zero in time to keep the temperature from going up less than 1.5 degrees C? Probably not. But we're going to do the best we can. And a lot of areas are saying, well, we don't want gas anymore. At least they're saying it in the United States. I don't know if that's the case in Indonesia or in other countries, but I think it is. I know it is in China, and I believe it is in Japan, and probably in Russia too. But total electric, let's get rid of gas. We don't want gas anymore. The methane that comes out of the gas pipelines, or even the gas that you have in your stove to cook on, there's a lot of methane. And methane is about 30 times as powerful as CO2. So these are the things that we're looking at. And a lot of that is in this climate change chapter, this new chapter that we wrote in the 2021 Handbook of Fundamentals. But operation and maintenance is really, as we've said a couple of times now, 30% of the buildings, of the brand new buildings, they lose all that efficiency, up to 30% in the first 3 years. So proper and ongoing maintenance, we are going to talk about in a little bit, and commissioning and recommissioning and retro commissioning. We will be talking about those things. But here's what a good maintenance strategy does. It reduces the energy and operating costs. It reduces the maintenance costs. And I'll show you the difference between reactive, preventive, and predictive maintenance. And you get this unscheduled downtime when you have a poor maintenance in a building. And it's you may not recognize this particular sentence, but reactive maintenance is, if it isn't broke, don't fix it. And we usually say, if it ain't broke, don't fix it. But this is the worst kind of maintenance that you can do. And yet, because there aren't enough maintenance people and building engineers in most buildings, that's the kind of maintenance that's performed. And so let's look at these three types of maintenance. And like it says, You got to convince the people who are paying the bill to change the way they do things. So here's maintenance cost per horsepower. And this is one, it's a little bit old, so these maintenance costs are going to be higher in all three today. But reactive maintenance is $18 per horsepower per year in a typical building. If you do preventive maintenance, then preventive is doing the kinds of things that you know you should do when you should do them, like changing filters, greasing bearings, those kinds of things. But predictive maintenance is what the manufacturer of the equipment says you should do. When you should grease the bearings, after how many hours should you grease the bearings, or in what temperatures, or what situations if there's a lot of dust, or this or that or the other thing. And look at it, it's $18 per horsepower per year for reactive versus about $8 per horsepower per year for predictive. So if you've got a fairly sizable building with 22,000 horsepower, $10 per horsepower is $20,000 a year in maintenance differential. And most building owners consider their building engineers and their maintenance people an expense. And they really should think of them as an asset, not an expense. They're very, very important. But if the year is bad and the building is not full of people and they're not making money on the building, they will start laying off maintenance people, which is absolutely the worst thing they can do. So one of the things we're going to look at, and it's going to be relatively quick, but you will have this presentation later. So how do you reduce the HVAC and other utility consumption? Well, here are some relatively inexpensive, some no cost, and others low cost. And you look at this and read it. I'm not going to go through these, but some of them are so simple. I mean, we've done energy audits on buildings. That third one that I put in bold a letter, adjust and repair economizer dampers. About half of you said that you do energy audits. If you are doing an energy audit, I almost guarantee that if there are multiple rooftop units or air handling systems in the building, some of them are going to have economizer dampers that don't work. The damper operator doesn't work, or it doesn't work properly. So you're bringing in more outside air at night when it should be shut off. And you've got a night setback thermostat that says, hey, come on, it's too cold in here. I set it for, 20 degrees or whatever it might be. And I'm bringing in maybe 0 degree outside air or less than 0 degree outside air. Now, you probably don't get less than 0 in Indonesia, do you? I would doubt it. But anyway, you're getting the much lower temperature or higher temperature on really warm days when it doesn't cool off as much at night than you should. So adjusting and repairing economizer dampers, cleaning or replacing filters when you should, optimizing start-stop of equipment, many, many units because of either bad control systems or bad settings or no control systems. So somebody has to do it manually, run 24 hours a day, 7 days a week. That is a tremendous waste of energy if nobody's in the building. You don't need to do that. So here's slightly higher cost. Use variable frequency drives on fans, chillers, pumps wherever you can. They're on steam jobs, there usually are many steam leaks. Traps aren't working properly. We've seen a lot of jobs where as things get changed on a steam system, the insulation gets taken off and it never gets put back on. And we'll have a couple of slides on replacing air handlers rather than replacing them, or using the new VRF systems. Here's higher cost ones. You get into variable flow chill water systems. A lot of the centrifugal chillers that are made today are oilless with magnetic bearings. So you eliminate a lot of the problems with centrifugal chillers. And of course, energy recovery heat exchangers will make a lot of difference. So here are some higher cost ones, additional higher cost ones, and geothermal, depending on what kind of soil and ground you have, can be very, very good because the average temperature stays pretty much the same all year round. Or underfloor air distribution, where you bring the air in low and raise it up. So it goes from the feet of the people up higher, so that if there is coronavirus or other kinds of problems in a building, they won't be basically having the air on one side of the room and the supply air on one side, return on the other side, and the supply air goes all across the room to get to the return. And anybody who's sick near the supply registers makes other people sick who aren't. So these are the kinds of things we have to think about today, because change is coming faster and faster, and climate change is making a lot of difference too. So the other thing that's happening because of the Internet of Things, instead of saying building energy management system, BEMS, we're saying and using building energy management information systems. And the gentleman who will be speaking about BELIMO and the little video you'll see will tell you a lot of good things about smart recommendations and complete integration of a building energy management system. So here are some things, though, that people normally don't consider. Sealing ducts. Many ducts leak a lot, and they can be sealed from the inside. And there are companies that make systems that you blow down the inside of a duct, and they can seal holes or separations up to a 1/2 inch wide or 1/2 inch large. The other one is, I say cleaning, cooling, heating, and condenser coils, but the word properly is the way to go and the thing to think about, because if you go into a lot of mechanical equipment rooms, what you have is a gate valve sitting there, a water valve with a garden hose on it and a garden hose nozzle. That's not the way to clean a cooling coil. I'll show you some slides. But this whole BEMS thing, Building Energy Management Information Systems, will give you a lot of good information, or give the building owner, facility manager, building engineer, a lot of good information, and tell them when things are operating well, when there might be a problem. The green light that says it's operating well and everything's fine might go to yellow or orange. And then if there's a real problem, it goes to red. And if the building engineer or the maintenance person sees that red light, they know there's a problem. And many times they can fix that problem before they get the "I'm too hot, I'm too cold" complaints, or "there's too much air, there's not enough air." This is what building engineers spend a lot of time on, these calls that are complaint type calls. So let's look at, I think, well, we'll talk about this a lot, proper and effective O&M practices. But here's a clogged filter. How much air is going to get through that filter? Well, some will, because the fan will pull it through. The static pressure is a whole lot higher. The proper amount of air isn't going to be going into the space. People aren't going to be happy. But if you don't clean it off relatively soon, here's what happens. How much filtration is going to be done by filters like this? Obviously not very much. But even when you put a new filter in, this sometimes happens. These are 2-foot long bag filters that aren't put in properly. Where's the air going to go? It's going to go right here, where it doesn't have to go through a filter. The air will go where it's the easiest place for it to go. And what happens when this kind of thing happens, or the one, or this one, here's what happens. All of a sudden, the coil that the filter is supposed to protect becomes like a coil. And what I said before about garden hoses and garden hose nozzles, this is how many maintenance people clean coils. So if you've got a 6-row deep coil and you spray it with cold water from a garden hose, what's going to happen with that dirt? You might clean off the first row, maybe even a little bit of the second row, but you're going to put a lot of that dirt right into the middle of the coil, if it's a 6-row coil or an 8-row coil. And then you go clean the back of it and you clean off the last couple rows, but the middle still has a lot of dirt in it. And here's what that dirt actually happens. You've got this biofilm on the coil, and that biofilm is really, it says, a black tar-like substance. And what it does is it collects that dirt, and it's very difficult to get it off. So when I say clean the coil properly, we were doing an energy audit on a 750,000 square foot building, which is pretty big. I should have changed it to metrics for you, but I didn't have the time. But anyway, it's a good sized building. And this is what it looked like before it was properly cleaned. And when we went down to, we were doing one of these ASHRAE building energy quotient audits on a beta test. And the contractor was there who was doing this. And the facility manager of the building said, "You got to come see this, Jim, because this is amazing." I said, "Well, what's happening?" He says, "You'll see. He's steam cleaning these coils." And I thought to myself, how do you clean a coil with high pressure steam without bending all the fins? This has got to be awful. So I go down there and this guy is spraying these coils up and down vertically. And I'm watching the coils to see how much they're moving back and forth. He had special nozzles. They didn't move at all. Well, I'm sure they did, but I couldn't see it. And I've got fairly decent eyesight. So this is the kind of cleaning you have to do. And EFM means environmentally friendly material, because he wouldn't tell me what it was. That's all I could get out of him. Let me take a look here. And then I think we can do a couple more slides before we take our 10-minute break. So I'm going to go through about 4 more. So the question is, we've been talking about all this HVAC stuff, but what else is there? Well, there's all these other things. Water efficient landscaping, no potable water use or no irrigation on the outside, using low flow waterless urinals or even waterless toilets, and low flow sink faucets, low flow showers. Another way to do it sometimes is shower with a friend. Sometimes that makes the showers longer though. So that's probably not a good idea. But the other thing that we want to look at is gray water. There's a lot of gray water in most buildings. Condensate from clean drain pans, water from sinks, water from washing machines and dishwashers, rainwater. Use that water and really cut down on the water bill. And where there's so much less rain coming down in some areas, this is something that we as engineers really need to look at and promote. But the other thing is you have to be careful. You know, we many years ago, I think it was the mid-90s. Yeah, mid-90s. We went from toilets that were 4 to 5 gallons per flush, 4 to 5 gallons per flush, to 1.6 gallons per flush. Now, buildings were designed with not that much of a pitch on the drain lines. So when we went from 4 or 5 gallons per flush to 1.6, plumbers made a lot of money because these lines filled up really fast. Newer buildings, they're designed for it. But when you have plugged up drain lines, this is not a good thing. And there's one more little thing, because we haven't talked about lighting, because we're not lighting people, but you know, everybody's changing to LEDs now. But here's another thought. Skylights, light shelves, light tubes. This is a light tube. I had several in my office. We built or designed a automobile sales and service building. We put these in because they weren't in the showroom itself, but they were in the offices that were right above the showroom where the people look down on the showroom. And on a sunny day, they never turn their lights on because you get a lot of light through these light tubes. And light shelves, of course, was kind of a lead, USGBC lead kind of thing, where you bring the outside light further in using something that it bounces off of and goes further into the building. So you don't have to have the perimeter lighting on during the daytime. This is where we're going to stop and take a little break. Hopefully you'll have some questions. We can have some discussion, or if you want to grab a fast bite to eat or go to the bathroom, this is the time to do it if you don't have any questions. But hopefully we'll have some good discussion. So
Thank you,
I will
Jim. Yeah.
turn it back to you guys and let me know if you have any questions.
Thank you, Jim. Well, we already have a question in line actually, but I would like to first probably give the opportunity if anyone would like to speak directly about their questions. There's actually 2 attendees raising hands. So let us, Mr. Songyot Swemong. Can committee give the opportunity for the participant to speak their question directly? Okay. Okay, maybe while the committee tried to.
Well, you know, some people don't like to be the first one to ask a question. So I will.
There already actually there are questions on the chat also here. Probably I will try to give you one of this from Irfan Nugraha of Wasco. I think his question relating on the reducing energy consumption in the building, and then his question is well, he already performed many times for the ducting leakage test as per DW 143 in the substation or modular building system. The question is how much we can expect the energy reductions by doing the I think the maintenance on the leakage there.
On the ducts, in other words, seal the ducts somewhat more, right?
Right. Yeah.
Okay.
Is it low cost, moderate, or higher cost on that?
Though that's actually a very moderate cost. Hopefully you have somebody in Indonesia who does that sort of thing. You know, it's going to be a lot more expensive if you have to bring them in from somewhere else. But I can check with the company in the United States that started this. It was actually done through they got money from the government to do it, because if you have a lot of leaks in a duct system, if you have leaks in the supply, then the proper amount of air isn't getting out to where it's supposed to go in the space. If you have leaks in the return, and the return is going through like a ceiling on towards the outside of the building or somewhere else, it's going through maybe some dirtier areas, you're picking up the heat in the return duct. So it makes the chiller or the compressors work that much harder, or it may plug up the filter faster if it's on the return side. So this is a relatively simple thing to do if you don't have to take the ceiling down. You know, I said there are companies that push this, whatever it is, through the ductwork, and it fills the holes in the spaces up to a ½ inch thick with this material. So you don't have to do a tremendous amount of taking down of ceilings and looking for where the leaks are, that sort of thing. It's automatic.
Okay. Thank you, Jim.
I hope that helped.
I think it is. I think you mentioned it's a moderate cost, and then as long as the testing, the leakage testing and fix is not too much effort to be put on the ceiling opening and so on.
Well,
Okay.
and then after you do it, you check out some of the air at the supply grills and that sort of thing, or check how much, do a testing and balancing of the building or the area and see how good do it before and after. Is the way you do it. And you see if you've got more air coming out, you know, and maybe the compressors aren't working as hard. So you want to do some before and after testing to see if it really did anything. Because if you don't have a lot of leaks, it's not going to do a whole lot. But you know, if you have a lot of complaints from people saying, gee, I'm just not getting enough air in my space, or you go into a building and you see everybody dressed very, very differently in a particular area, because some people are too warm, some people are too cold, and you know there's a problem there. Is it a temperature problem, or is it an amount of air problem?
Okay, thank you. So the next opportunity can be given to Mr. William Yo. Do you want to speak yourself on the questions? Can the committee, William Yo, I think you raise your hand. You want to ask question directly? You're still mute over there. Okay, let's to the next one, Pak Dedi. Can committee open the mic for Pak Dedi? Pak Dedi, welcome Pak Dedi.
Hello, Pak
Go ahead.
Adriansa.
Yeah.
Thank you. Good morning, Tim. How are you in the States?
For me, it's very late at night.
And very cold, of course, right?
Yeah. But I'm good. I'm good.
Okay.
I'm ready for this.
I'm interesting. You are saying the tube cleaning or coil cleaning using the AFM, correct?
Yes.
Yeah. So can you give me a sample of what kind of what type or what brand? It doesn't mean that I'm asking for the commercial issue, but give me the sample of material of AFM, for example, it states.
Well, okay. What this fellow does, he has a small portable steam boiler. And of course it goes to his hose and then to his nozzles. And he does, the way he used to do it was he would put just straight steam on the coil, which is what I was seeing when I first went to the second sub basement where he was working when we were doing this ASHRAE Building Energy Quotient study. And he was just going up and down with this steam, which was really getting through. It wasn't pushing the first 2 rows into the middle. It was, because it was high pressure steam, it was actually pushing it to the back of the coil. But then he cleaned the back of the coil the same way. And then when he finished doing that with the straight steam, he went back to his steam boiler and he took this secret environmentally friendly ingredient, which I still don't know what it is because he won't tell me. And he put it in and he cleaned the coils again. And if you remember that slide I showed you with the biofilm on it, this biofilm, because of this material that took away the biofilm, it was, I'm glad I didn't have something to eat right before I went to see it, because it was really terrible to look at. It was black, it was really filthy, dirty, but that was that biofilm that came off the coil. So that coil, when he got done, was as good as new. So not only did you have a lower static pressure drop, but you had a much better heat transfer between the chill water in the coil or the refrigerant in the coil and the air. So it made a lot less energy use on the compressors. But that's as much as I can tell you.
Okay, thank you, Jim. Because based on my experience, if we have a big air handling unit size of 15 to 50 tons, it takes approximately 3 or 4 days to clean because of the row is very big. Yeah, 5 rows and very difficult. Yeah. So that's
Well, where you are, you probably have 10-row coils too, right?
yeah.
Yeah.
Okay.
Those are the worst.
For your answer.
Thank you, Pak Dedi. Thank you very much. So I think we still have about 1 or 2 minutes, just a general question, but I think many participants asked about this. You talk about you write about the climate change section on that, talk about the sustainability and then energy and everything. So in your opinion, Jim, what will be the net zero energy building, especially on the operation side? What's your view on it?
Okay,
that's the
well,
question.
all right. Well, my view is it's certainly the way to go, but engineers have to be very careful. And this is what we talk about in the climate change chapter that we wrote, close to a year ago now, which just came out in June of 2021, is that engineers have to think about well, you still have to think about what the design temperature is that you've been using for years and years, but you have to look at what's the future design temperature going to be? What do we have to do with our buildings to make them more sustainable and more resilient to hurricanes and tornadoes and the floods and everything and wildfires too. I don't know if you have too much trouble with them in Indonesia, but there certainly is a lot of trouble in Australia and the United States and other areas with wildfires. But net zero is what we're looking at. And actually, we're already starting to look at net negative. So you're using enough, a low net zero, and net zero is not net zero all the time, because there are going to be sometimes you have to use more energy. Sometimes you can use less energy, but overall, the entire year, you want to get to that net zero point by actually using a lot less energy in certain times, or using renewable energy, whether it's solar photovoltaic or solar thermal, which is much more efficient than photovoltaic, using solar thermal where we can, and using wind energy. There are some wind turbines that are not these huge ones that have these great big airfoil blades and what have you, and use a lot of energy. And if you need 10 of them, you really have to have 11, because one is always breaking down. And that's what happens. The maintenance on those is terrible, and it's very tough. I mean, you think about it, would you want to be up on top of one of those 200, 250 feet high wind turbines and be maintaining it? Very tricky, very difficult, and very expensive. So, we have these meetings every year, these COP meetings, and they say, well, we gotta keep it under 1.5 degrees C, and we're already past that point.
I
So
see.
what we need to do is a whole lot more than we have been doing to try and keep it under 2 by 2050, because the amount of methane, the amount of CO2, the amount of refrigerant gases, all the greenhouse gas emissions are way higher than they need to be. And there certainly are people all over the world who don't believe this. But how you cannot believe it when we have some islands that are, people are already having to move out of them and move to a higher island, because every time high tide comes, they're losing more and more pieces of property. And we have you undoubtedly, Indonesia being what it is, have a lot of that along your coastlines. You have those bays that really come off the sea that are going to get higher. And we have to be aware of those kinds of things. And I tell people here, please don't put your mechanical and electrical rooms in the sub basement. At least have them on the first floor, if not higher than that. Sure, you're going to use up some rentable space, but what happens if you get flooded and you're in a sub basement? You don't have any heating and air conditioning maybe for a month or for 2 months. What's that going to do to your income? So spend a little bit more money up front and do it the way it needs to be done today.
Thank you, Jim. Well, that's really, really true for Indonesia, especially as you mentioned, we have a lot of also the impact of the climate change, because we are archipelagos, we are island country, and then we had actually forest fire almost every year.
Oh, you do?
Yeah, we have that. So we have to, of course, come to a solution on that by optimizing the AIQ performance, also as well as the energy performance of that system. So
well, and the problem is, because of this coronavirus,
right,
society says you got to bring, society, I mean ASHRAE Society says you got to bring more outside air in.
right, yeah.
How do you do that when you have all this smoke from a forest fire? You don't. You want to shut down the outside air. And there are air cleaning technologies that we'll talk about in a little while that where you can do that.
Okay. I think this is a good time to continue to the next sessions. Oh, I just want to let the participant know that the material of the presentation is available to share. Thank you very much, Jim, for allowing us to share your presentations. So,
my pleasure.
Thank you. So please, Jim, you can start for your second session.
Okie doke. Oops. I'm probably going to have to share again. And there we go. Okay. Answer me this. I put in EPA portfolio manager Energy Star analysis. That's a American thing, that Energy Star and Energy EPA. Do you use any of that there?
Well, some of us, the ASHRAE member, have that, I believe. We have also the regional regulation for building energy managers. This is from the Ministry of Energy and Mineral Resources. So I think it's kind of like similar in some way.
Okay. Okay. So hopefully a lot of your building owners, because when we had the slide about energy audit, I think it came out about 50-50, yes, no. No, I think it was high. I think it was more people do energy audits than don't, or knew about them, or have done them with their organization. So ASHRAE came out several years ago now with this building. It's probably 10 or 11 years now that I'm trying to think when we did the beta test. Building energy quotient. And it rates buildings probably in more areas relative to indoor air quality, not just straight energy, but also IAQ than a lot of these other things do. And so let's just look at what an energy audit actually does. Whoops. We got to go back. How do I do this? Down at the bottom. Usually there's something that says go to the last slide, and I'm not finding it. Ah, well. Okay, here we go. All right, I knew I'd get it eventually. So ASHRAE has 3 levels of energy audit. And the very first one, which is really simple, is examine the utility bills before utility bills say for gas, for electricity, and for water. And then this level 1 audit is a relatively inexpensive audit. It's called a walk-through analysis because basically you walk through the building and you look at what's going on. You look to see, for instance, if in a particular area, people are wearing all different kinds of clothing because some are too cold and some are too warm. But level 2 is what most people want, is a real energy survey and an analysis of what should be done, how much it costs, and what's the payback. Those are the kinds of things that a level 2 audit does. And level 3 gives you more information on payback, so you can go to a bank or some investor and get money to do it. But most people are fine with the level 2. So what does it look? What do we look at? Here's what we look at. Forget the asterisks because that was for a particular United States Energy Policy Act in 2005. And we looked at those first 4 items, and the government paid up to $1.80 per square foot for the entire building. 60 cents for the envelope, 60 cents for lighting, and 60 cents for HVAC, if you could improve it enough to get to the payment. But these are all the things that you look at and needs to be looked at, and when you're doing an energy audit. So here's what it does. You collect and analyze the data, you study the building, how it operates, what are the characteristics of the systems, and you look at what modifications they can do to reduce the energy use and reduce the cost. And then you look at what I said before, you look at how much is it going to cost, what's the payback going to be, and you list it. And if you say item number 2 and item number 4, if you put them together, they'll be better because you'll save more money and it won't cost you as much to do number 2 and number 4 or number 1 and number 6, whatever it is. And you make a report up, and hopefully they do something about it. You don't want the report to be too long. You want the results of the report to be maybe only 3-4 pages. And then if you want to have a lot of information afterwards, that's good, but you've got to get them in the first 3-4 pages. And people who look at these reports, these are now the building owners, the facility managers, they don't really understand kilowatts. They don't really understand BTUs, most of them. You've got to talk in their language. You've got to talk in savings, net savings, internal rate of return, all those kinds of things, which ASHRAE talks about in their book on basically doing energy audits. So let's talk about for just a second here, why do building owners turn down energy audits? And many building owners turn them down. Well, the cost of the audit may be too high for them, but typically it's hardly the highest cost in the audit. What they're concerned about is what you're going to tell us to do after you do the audit and give us this report. And if you think back to 2008, 2009, 2010, BOMA Detroit asked me to become chair of their Energy Conservation Committee. And I didn't really want the job. I didn't really need the job. I mean, obviously it's not a job. It's a job, but it's free. And I just didn't have the time. But they beat me up pretty good. And I finally took it. And I said, I will do it, provided you have mostly building owners on my committee. I don't want anybody but a building owner on the committee. So they said, yeah, we'll do that. Okay, that'll be fine. And they said to me, Jim, you've been asking us why we don't do building energy audits. Here's the answer. It's real simple. Our buildings, we're lucky if they're 65% occupied. At 65%, we're not making any money. We're losing money every month. So what are we concerned about? We're concerned about the leaky roofs. We're concerned about the crumbling parking lots. We don't, energy comes in, it's a bill every month. It's not that big. We don't have the time for this. We don't have as many, like I said before, we don't have as many maintenance people as we had because we weren't making money. So we laid some of them off. They're not here anymore. We don't have people who can really do what you're going to tell us needs to be done. And here's the other thing. It's really fear. You have to think about when you talk to a building owner or facility manager or building, what do they really want? What do they really need? We did one a university campus, and they had a particular one building we did was an administration building that was really in bad. It was fairly new, so it wasn't in bad shape, but the HVAC system was terrible. It really wasn't working well, wasn't being taken care of. And we got through with the audit, and the building engineer pulled me aside and he said, Jim, am I going to get fired? That's what he was afraid of, because he wasn't doing a good job. He wasn't doing a good job, not because he didn't know, but because he didn't he didn't have the time to take care of 6 buildings and really know what was going on in those buildings. And my answer to him was absolutely not. What we're going to do is give your owner this information and say, you need more people. This guy can't do the job. You're killing him. I mean, he may not even last that long because he's trying to do the best he can in 6 buildings and he can't do it because you've taken all his people away. So we're going to help you and try to get you more money and more people. The real key, if we look at what else, here's what else. That's what happens. I mean, people put their head in the sand and they don't really know what's actually happening. So here's another thing. What do we do after an audit? Well, we recommission or retro commission the building based on the results. If they want us to do it, fine. They want somebody else to want a contractor to come in that they're familiar with to do it, that's fine. But the key is doing this O&M, and you've got to do it all the time, and remove and replace inefficient HVAC and water systems. It's ongoing commissioning. On another presentation I have basically on audits and commissioning, I have a slide that shows when you do an energy audit and commission the building, the systems in the building, how the energy use goes down, and then it starts to go back up again. And then you do another audit 3, 4, 5 years later, and it goes back down. But if you do ongoing commissioning after the first audit, it's very inexpensive. And you're going to have to figure out, what do I really mean by inexpensive? And it'll be different in different buildings, but it's a lot less expensive than that first retrofit, that first commissioning. Recommissioning is much less expensive than the first one. So that's the way that goes. So let's look at who gets blamed for poor indoor air quality? Well, here's who gets blamed. Everybody who's at all involved with that building, from the architect to the real estate broker, to the building management people, to even the landlords, tenants, and employers. Everybody gets blamed for poor IAQ. We don't do any design work anymore, but we carry very healthy insurance on errors and omissions, because we know if there's going to be a problem and we've been involved in something to do with that building, we're going to get hit as part of that lawsuit too. So what does our owner do? Well, we did a building. Responding immediately is very, very important. That's really key to what's going on. We did a building that we got a LEED. It was an existing building. We got them a LEED certification of gold, which is very, very good for an existing building. But if you don't respond immediately, here's what happens. The one person who thinks there's a problem, and there may be a problem, there may not. Notice the next thing that says perception is reality to the person with the perception. They think there's a problem. They think there's a problem. And they talk to somebody else. They talk to their next door neighbor who's in the cubicle next door to them. And then you get two people talking about it. 2 goes to 4, 4 goes to 8, until you have what's called mass psychogenic illness. It's in people's heads, even though there's not a problem. And this building that we got LEED Gold for, they had a problem. We got them this wonderful certification, and about a year later, a fan coil unit in the ceiling of a particular area, the condensate drain got plugged up. So the fan coil, the drain pan overflowed naturally, got the ceiling tile dirty, wet and dirty, and it got the wall wet and dirty. They fixed it right away. There was no problem. A month later, somebody says, you know, I come in here now and I get headaches and I get stuffy nose and all the time. And they called us. They said, we did everything well. We know we got everything, but people think there's still a problem. Will you come in and help us? Well, we don't do IAQ analyses. So I got a testing company to do it that we work with. And they made up a nice report. We went in and we gave the owner the report. The owner showed the report to the people and they were satisfied. But they said, we shouldn't do this, the owner. We shouldn't make the report because they're not going to believe us. All they're going to want to think is, well, here's the kind of things they think. If the owner can't identify the problem and they knew what the problem was, or their mitigation efforts were not successful, then you need some kind of air sampling. And by the way, just so you know, air sampling at one point of time is only sampling the air at that particular point of time. If you're going to do air sampling, it needs to be done over 24 hours. That's what good air sampling is. So if somebody comes in with a couple of petri dishes, and they say, oh, we'll sample it, we'll take it to the lab, we'll sample it, we'll give you what's going on, and they do it at whatever time they do it, it might not be the time where there really is a problem. So if you get involved in any of these, make sure whoever you use, or if you do it yourself, then it's got to be more than sampling at one time. So that's what goes on there. So let's look at, I told you we talk a little bit about HVAC and COVID, whatever the coronavirus happens to be. Now it went from BA.1 to BA.2, which seems to be really sweeping all the countries these days. It hit England a few weeks ago. It's now pretty rampant in the United States. Have you had that variant of coronavirus in Indonesia yet? Anybody want to answer? Anybody no to answer that. It's caught much easier than the Delta variant of it, and it doesn't seem to be as serious. And if people have been vaccinated twice and then got the third vaccination, it doesn't seem to affect them all that badly, is what we found. But let's talk a little bit about IAQ techniques and systems and relative humidity, because that's real important. And I'm going to show you this relative humidity slide first. Some of you may know that ASHRAE recommends 40 to 60%. That was done back in 1985. It was a study from Canada that ASHRAE paid for, and he found that 40 to 60%, if you look at this chart, practically everything goes to zero or starts at near zero in that 40 to 50% range, but it's an unrealistic range. So what we did, we modified that chart and made it go down to 30%, because what's the actual design winter temperature? I mean, I know you go up to 14,000 feet in your mountains, but where the most of the people are, like Jakarta, for instance, what's the design winter temperature?
Well, we don't have winter one, so the design is around 35, I believe.
It's what?
35.
5?
The outdoor conditions, outdoor design conditions.
Okay, I'm
The
not
indoor
hearing you. I'm not hearing you well.
Sorry, what was your question? The indoor design conditions?
Yeah, what's the design conditions say at 1% in the wintertime?
I think it's like 25 C on this.
25, okay, 25
Celsius.
No, 25 C, not in the wintertime, is it?
We don't have winter here, so we have the
Oh, that's right.
whole thing.
Okay, so you're saying the average temperature
Right.
is 25 is
Yeah.
50, 45 is 77 Fahrenheit.
Right.
Okay, so the temperature outside my window right now is 5. I looked at that before this started. So I got to tell them what the temperature. It's warm. It's really warm for the end of winter, actually. Although it's going to be up to 10, I think, tomorrow or the day after. But anyway, here's what happens. And okay, this is relative humidity. What happens is if you get much more than, well, you don't have to worry about it, 40 to 60, you're more concerned with keeping it under 60% than you are with keeping it above 40%, aren't you? So you have a cooling problem, not a heating problem. So what I was going to say about areas that are cold, like where we are, you can't go to 40% because you'll have water coming off the windows and the walls from the condensation. So this slide, really, if you can keep it in that 50 to 60% range with good HVAC and good cooling, you're doing very, very well. But okay. ASHRAE started talking about the coronavirus being carried on the airstreams fairly early in the game. The World Health Organization didn't really get it until after August of 2020. And by that time, there were a lot of things that pointed to it's being carried in the air. Church choirs, people were getting sick all over the place because you're singing. And if you've got COVID-19, then you're giving it to all the people around you, especially in front of you as you're singing. And it took the World Health Organization a long time to realize that, because they're mostly doctors. You know, they're epidemiologists. They're doctors who don't think about this sort of thing. They're thinking about the people and what's happening to the people. So what we're looking at is these kinds of things. Now, this is going to be, my guess is, tell me if I'm wrong, this is going to be very tough to read. Is this difficult to read or not?
Well, it is.
I think
It takes some time.
it's probably pretty difficult. What I'll do when we redo this, you'll be able to see it. Oh no, you won't, because the slides will be different. I will break this chart down to about 6 different slides. And what this says is on the left side is all the things that these various technologies do, like inactivate virus, inactivate bacteria and other germs, eliminate most volatile organic compounds, and reduce odors, produces ozone. There's some yeses and nos here. And on the left side, you can probably read the words traditional technologies, higher MERV rated media filters, chemical filtration. Then the middle one is newer technologies, and that actually goes from the 3rd vertical silo over to the end. And we've got ultraviolet germicidal radiation, and I'm going to show you a picture of that. And then bipolar ionization, I'll show you a picture of that. And the rest of them are various kinds of things associated with that. And I have a lot of notes down here so that Newman Consulting Group doesn't get in trouble. But I will send this all to you as a separate email. But here's ultraviolet. And do you use this at all in Indonesia, ultraviolet? You probably do to some extent.
Yeah. Some building use it.
Okay, so you've got these ultraviolet lamps and the air has to go over the lamp. This is called passive as opposed to active, which I'm going to show you next. But the air has to travel over the ultraviolet lamps. It doesn't go into the space, although there are some newer systems that do go into the space that are used in hospitals but can be used in other areas too. The next one is called bipolar ionization. What it does, it breaks up the electrons into positive and negative electrons or ions. And they react with pretty much everything. The positive ones will react with negative ones in the space, and the negative ones will react with the positive ones in the space. And they attract each other, and some of them will do what we call agglomerate the particulate, which is make it kind of stick together and get larger. So it either falls on the floor where it's not hurting anybody, except in a home, it might hurt the kids who are crawling around on the floor, but in a commercial office building, there's nothing wrong with that as long as the proper cleaning is done. But some of it will go into the air and go into the return grill and get back to the HVAC system. But the tube type bipolar ions will last from 30 seconds to 5 minutes. And they're constantly being generated in the air handling unit and put out into the space. So there's all these new fresh bipolar ions in the space. That's called an active system. It's actually going out and doing something. The air doesn't have to go over it, as opposed to the passive ultraviolet system. So it's a good system. It's not super expensive. And it doesn't cost as much to replace the bipolar ionizer as the UV does. But with all of that, the really important thing to remember is you can't depend on any one of these things to be the answer to the problem. So any salesperson who comes in and says, you put my system in and you're not going to have any problems, that's not quite true. So the other thing that's happening, I'm watching the time carefully here, we're almost done, is around here, and I don't know if you're doing it. I think you said you were doing it in Jakarta. They're looking at what the city buildings are using energy-wise and making them report their EUI, their energy usage index, if you will. And if it's higher than whatever, and hopefully it's a good city commission that's looking at this, and ASHRAE people are helping them. This is where we come in real handy to some of these things, is say, here, this is good, this is not so good. And what smart building owners are doing is hiring ASHRAE type people who understand HVAC, to help them conserve energy and figuring out how to pay for it and doing what we recommend to be done. So here are some areas to get information, a lot from ASHRAE, of course, some from many other organizations, like US Green Building Council has some good information on their lead for existing buildings. BOMA does. I'm a member of Committee on the Environment with AIA and IFMA. Energy Star, this EPA Energy Star. It would be worthwhile to look at that. It's a tough website because there's so much on it. But if you go to energystar.org, it's you'll get a lot of good information. And here's some others. Forget Pace Nation because you don't have that in Indonesia, but these other ones are pretty good. And of course, there's a little. We have a lot of information on our website. We made it a resource-rich website. But here's what I told you. You would find these two articles. One of them is that one I wrote for Building Operating Management magazine, and another one is that I wrote this a few years back, but it's in our blood. These may not be. No, they're not in the blogs on our website, but they're on our website somewhere. But anyway, the real key here is check out that article because a lot of the one on sustainability and resilience came from that Building Operating Management September issue and came from the climate change chapter in the 2021 handbook. So again, we talked. How'd that happen? Oh, okay. This is why people change, and in reality, these are all happening today, and they're happening faster and faster. This kind of ties in with what we've been talking about, and what I asked you to think about. This whole balancing act thing. What can you do to influence some of these things? And here's another quote. Oh, this is a different quote. All right, I had a quote from Tim Wentz, who was a recent ASHRAE chapter, ASHRAE Society president, that says the greatest challenge we face today is failure to adapt to change. And this one, think about the dinosaurs. It's not the strongest species that survive, nor the most intelligent, but the ones most responsive to change. And there's a lot of change going on, and we have to do that too, or we're not going to survive too well either. Oh, there it is. I thought I had left it off. So we need to think about what we're going to do. And with that, let's see if we have any more questions now that we can answer during this next 10 minutes. Look at that, 11:06. So it's 10:06 for you guys. Good. We finished 2 minutes early.
Yes. Thank you very much. But we already
Do you have any questions there?
No, we have already here.
Okay.
Yeah, it's really relevant to.
If you could talk a little bit louder, because I'm having trouble hearing you.
Okay. Sorry,
much
I think,
better, much better.
Okay, good. So there is already questions. I think this is from Mr. Randy Putra. regarding the relative humidity for the comfort zones, it's about 40 to 50%. But we have a dry room, like in the clean rooms, that maintain the relative humidity less than 20%. Oh, this is just us in your experience. Where the person or operator shall be doing the activity on the maintenance of that kind of room. And do we have any international standard to refer to? So I think this is about the maintenance of a clean room, which has the low humidity.
Yes, yeah,
Oh.
and 20, there are clean rooms that want higher humidities. It really depends on what they're doing in the clean room itself. 20% tends to be a little low, but that's so they're not doing anything with moisture affecting what they're doing in that particular clean room. And the way you do that is, you know, with proper HVAC, without knowing what the process is, it's kind of tough. But the question was, where do we find something on that? There have to, and I can't answer that one off the top of my head, but there have to be sites, you know, HVAC sites and clean room sites. And I know a number of people who design clean rooms. In fact, I almost went to work for one of them many, many, many years ago when I first started in this business. A clean room, well, the clean room manufacturer says, here's what I want. You tell me how to get it. They don't really tell you how to do it. So it's a matter, usually in that case, especially where you are, it would be subcooling the leaving air temperature off your HVAC system and then reheating it so that it's at a comfortable temperature. But by subcooling and reheating, you're lowering the absolute humidity and the relative humidity of that air. There's also another way to do it, which would be through a desiccant. And a desiccant adsorbs moisture, adsorbs, not absorbs, AD, so RBS as opposed to AB. And we use that a lot in the States and probably elsewhere for growing cannabis, you know, marijuana. And if you use a desiccant to absorb the water rather than a standard commercial cooling system, it's a much better way to do it.
Okay, thanks,
That
Jim.
might be an answer to getting it down to 20%.
Right,
That's
yeah.
tough that's easy for a dessiccant to do.
So desiccant is one of the solutions
Yep.
on this case. Okay. And then there should be like the question is related to whether there should be a person or operator inside the room, or it should be mainly empty. That's the question. So
again, it depends on the design of the room and what's happening in the room. But one of the key things in a clean room is the proper operation of the air, where the supply and where the air is brought into the room and where it's exhausted from the room and how many air changes per hour there are. And in a clean room, they're usually pretty high. So should there be a person in the room taking care of it? Probably not. It should probably be taken care of from outside the room, but you have to have the sensors inside the room so you know what to do outside the room to keep it at that particular temperature and humidity.
Okay. Okay, let's move to the next questions. From Ting Jui Sun, can you explain what's the difference between level 3 energy audit and retro commissioning?
Okay, they're both very different. and whether it's a level 1, 2, or 3, and retro commissioning. And that's a good question, because you've got to be careful when you retro commission and not necessarily bring it back to the original design conditions, because the building itself may have changed somewhat, or what you're retro commissioning, changing in the HVAC system might be for a completely different purpose than it was originally designed for. So you have to look at what the original design was and decide, should you bring it back to the original design, or should you bring it to what's being done there now that might be different from the original design. So that's the retro commissioning or recommissioning. But commissioning itself is making sure the system is operating properly like it's supposed to be, with either what you recommended in the level 1, 2, or level 2 or 3 energy audit. You recommended something, and then you commission it when the contractor has finished making the changes, to make sure it's operating properly as to what you said it should be doing. Now, I hope that answered the question. I'm not sure.
Yeah, I think that's more or less like explaining the difference on that. A follow-up question on that. How do you estimate the cost of the retro commissioning? What will be, is there any kind of like a reference or a function of building energy costs or anything else?
Okay.
Can you give any, because you're on the consulting also on that, I believe.
Yeah.
Go ahead, please.
And I'll tell you what we really do is we get a price from a contractor.
Well, there are building owners here too. Maybe they want to have a budget on it, so they need some.
Well, and
Okay.
that's, well, actually, that's what a good energy audit does.
Okay.
A level 2 energy audit will give you the budget. But what we do to come up with a good level 2 energy audit, or level 3, which is more intense, we typically will, either we know about what it's going to cost, or we actually go to a contractor. For instance, costs in the United States have gone up by anywhere from 20 to 30% over what they were a year ago, because of all this, not being able to get ships in from China or wherever. And, the constriction of the supply chain has really hurt building costs. And lumber, for instance, doubled. Steel doubled. I mean, so a lot of budgets that were made a couple of years ago before the coronavirus, oh, it's been awful. I mean, and a lot of projects haven't happened. We had 6 projects at the beginning of 2020 that none of them happened. The banks stopped loaning money, and the people who were going to do it said, I can't afford to do this. I budgeted, $2 million for this project, and it's going to cost 3. It doesn't make sense. We're not going to make any money. We're going to lose money on it, even after we get people in it, for $3 million. So those costs have come down a little bit, but not a lot. So construction has changed. And the other thing that's happened here, I don't know if you have this problem, maybe not, but we can't find people to do the work.
Oh, we have a lot of people here who wants to do the work. I think that's the opposite condition on it, but yeah.
Well, we're having problem finding people. So the unions have really stepped up to the plate and are training people faster. Instead of 2 years, they're doing it in, like 6 months or 9 months, but less than a year. They've cut the training in half, but to try and get more people out there doing things. But it's been really tough.
Yep. Okay. Well, I think let's bring me to about the competency that you mentioned, we have a lot of actually like the one who comes today is about more than 180 person. It showed the interest on this energy audit and also the retro commissioning. Do you have any suggestions on the appropriate trainings for the people who are interested to either practice as energy auditor or for building owners or even contractor example?
Okay, okay. Well, that's a good question, because some contractors will do energy audits. Those are typically contractors who don't just do read a plan and specification and quote on it and try and get it because somebody's already done the design on it, and they, you know, it's a standard plan and spec job. They are design build, what we call design build contractors. Well, they will do their own design work because they may have an engineer on staff or some people who are very, very smart, who know design and really know HVAC systems because they've been working on them for, you know, 5 or 10 or 15 or 20 years. So they know what a system should look like. So a lot of these contractors are design, build, and service contractors. So they can design a system, they can build it, and then they can service it and do good operations and maintenance. But typically, the people who do a lot of this are the design engineers who have been designing HVAC systems for some years. And so when they go out to look at one, they can tell if it's operating properly or not, especially if they designed it. But they know if it's operating up to specs. But that's what commissioning is all about. And a lot of building owners don't like to do commissioning because it costs some money to do it, of course. But those who have done it and find out how much it saves them, typically a good commissioning agent or good commissioning organization can save as much as they cost probably in the first 2 years of the building operation. Because if you remember those early slides, 30% of building operation is waste within 3 years. 30% within 3 years. So if a commissioning agent costs $10,000, they may have saved well over $10,000 in operating costs in those first 2 or 3 years. So commissioning has to be sold, and owners who use it either with a new building or with older buildings. We just did one last year for an older building, and they had a 900-ton chiller that didn't work. So while we were doing the commissioning, they had 2 900-ton chillers. They had, duplication, but one of them didn't work at all. And they found, and we found, of course, that they could, and we had a couple of weeks of really a lot of high heat with only 900 tons instead of 1,800. And because so many systems, both for heating and for cooling, are so far oversized, they didn't need another 900-ton chiller. So they put in a 500-ton chiller, and they said, okay, if the 900 goes, we still got 500 left, and that's better than nothing. But we'll use 500 for the shoulder seasons, for the spring and the fall, not the super hot in the summer, because we'll need 900 tons then or more, because they ran that 9 for 24/7 for 2 weeks and really messed up our energy on it. But those are the kinds of things that we need to think about as design engineers. We need to think about having more than one chiller, more than one, well, you don't use boilers too much, but more than one boiler where it's cold, or backup systems. But one of the biggest things is making sure the economizer is working right, and making sure the filters are changed, in reasonable times. Those are the kinds of things, those are, pretty basic.
Right. Yeah. But I think they are needed to be implemented, need to be optimized, even though that's basic. For example, there is another question about the VSD or variable speed drive
Okay.
or the variable frequency drive. That seems to be basic to be set or optimized according to the operations. I think that's one example also that the contractor or the installer have to perform on it.
Oh, absolutely. And
Yeah.
and in fact, the way we found this out on this particular administration building on this campus where the guy thought he was going to get fired, the variable frequency drives on, this was now, oh, let's see, 20 degrees would be what? Probably around -5°C or something like that. But the variable frequency drives in the middle of the winter, they're normally 60 hertz, and they were operating at 55 to 58 hertz. It's like, why are they operating so high? They should be operating at 40 to
Yeah.
45 because you don't need as much air in the wintertime as you do in the summertime. And so when we opened the first one up, the outside air damper was open 60%, and it was about a, it was probably a -5°C day,
Okay.
and they were open at 60%. They should have been open at 10. So they were bringing in 80% outside air. So their heating bill was terrible,
Right.
and it was running like that all night long. 7 days a
Okay.
week.
Okay, Jim, thank you very much for your insights. I think we have gained a lot of informations and also experience from what you share. Thank you very much, and I think you can take a break. We're going to continue to our next speaker, Mr. Alvin Chan. Mr. Alvin Chan, are you ready?
Yeah, I am.
Hello, good morning.
Hi.
Still also
Morning.
in Malaysia, it's still morning, right? Mr. Alvin Chan is a regional application consultant of Belimo. It's an automation product company from Malaysia. It's a subsidiary of Belimo Automations from Switzerland. And then Alvin is responsible for Belimo Technical Solution in Southeast Asia. He has 22 years working experience in HVAC and in the technical roles mainly, and then started his career in facilities maintenance in the semiconductor factory, then trucks to R&D manager and air water product specialist, and also ME consultant. And then he also has worked in various types of projects in Southeast Asia, China, Hong Kong, and Middle East. I think I should be in bahasa on this one. Jadi Pak Alvin sudah 22 tahun pengalamannya, mulai dari pabrik semikonduktor sampai manajer riset, manajer litbang, kemudian sempat juga di konsultan ME, dan dia bekerja di Asia Tenggara, ya, Bapak dan Ibu, Cina, Hong Kong, dan juga Timur Tengah di sini. Pak Alvin ini mempunyai latar belakang pendidikan mechanical dan material dari National University of Malaysia dan sudah menjadi anggota ASHRAE sejak 2006. Pak Alvin akan mempresentasikan tentang Belimo Product Solution untuk otomasi dan termasuk juga yang sudah dalam hubungannya dengan energi audit maupun untuk commissioning ya di gedung. So, Mr. Alvin Chan, the floor is yours. You have about 30 minutes to present this one.
Yes, thanks, Adi. Thanks for the introduction. Good morning, everyone. I'll do an introduction to you about what's available today as advanced field devices that supports efficient commissioning, retro commissioning, ensuring optimal building efficiency. And this is the agenda for today. I'll talk about PICV, VAV, and sensors. So these are the three products or solutions that are grouped as field devices, and including a thermal energy meter or TEM. And we look at integrated PI valves and TEM. So this is something new. And smart devices, not just field devices anymore. So the field devices which comes with some controls in them, and utilizing that the sensors that's built in there, and then integration with cloud, and using the power of cloud to enhance the performance of these smart devices. On the left here is a traditional setup where you have balancing valve and traditional control valves. And on the right here, you have PICV, or pressure independent control valve. So for traditional valves in a variable flow system, there is actually a lot of issues that you have to face. The first of them is balancing valve. You need to set this correctly, and it is very time consuming. So you need to set this one by one. So in this example, you see only 4 branches, but in an actual building, there could be hundreds of valves, and this is very time consuming. So you have to go there and set it up one by one. Without the control balancing valves, the water wouldn't be distributed evenly, and then you have hot overflow, okay, or underflow. So if it's overflowing, then it's too cold. If underflow, then it stays too warm. And this system is only balanced at the design or the maximum flow. So it's not balanced at part flow. When it's not balanced at part flow, it means that you will have that overflow and underflow situation. And next, over here, you see the valve authority calculation for the control valves. So normally, people would just select the valve pressure drop or the KVS value or CV value based on the coil. But I mean, if it's for this example, this branch, the authority is still good. But if the pressure across the branch is much higher, as it is closer to the pump, you will see that the valve authority becomes bad, and this becomes a control issue. So what happens here is that the valve no longer functions as a modulating valve. It becomes an on-off valve most of the time. And this will present a control problem here. You will have overflow and low delta T issues. And next is if I were to modify this building, okay, so if I add or take away any branches, you need to rebalance the whole setup, okay? So, but normally people won't do that, and that's why you have a poorer performing building, which, you know, like Jim explained just now, the efficiency drops. So this happens quite often because when you have a new building, it's not 100% occupied immediately. So normally the occupation of the building will be in phases, and you find that you actually need to commission it as you occupy it, but probably I think most of the time that's not done properly, and then you have a building which is inefficient. And the static balancing valve poses energy loss. So as you can see here, they've been set to these pressure drops here. So at part flow, you will still get this pressure drop, which means that you are wasting energy in your circulation system or the pump all the time. And all this problem can be easily fixed. Basically, all the things which I mentioned just now, you just need to use pressure independent control valve. So you have good control, and you have good energy efficiency. How you control the pump is by using this differential pressure sensor here. So as the valves modulate close according to the load, as the load reduces, the pump will reduce in speed, and it reduces the flow, it reduces the pump head, thereby saving you energy. All right. So the pump power calculation is fairly simple. It is the pump head multiply the flow and multiply the divided by the efficiency. So as your pump head goes down, your flow goes down, and therefore you save energy. So that's why we have variable flow system. And as I explain further, as I go into air system, you will see a lot of parallels between air and water system and how we save energy or optimize. And here are just some notes for you to refer to later. Okay, so these things I've mentioned just now. And for application wise, for a PI valve, you need to check at the index branch that the differential pressure is not less than the minimum required by the valve. And for the branch nearest to the pump, that it doesn't exceed the specification of the PI valve. And for energy efficiency, the differential pressure must be located at the furthest branch to maximize the energy efficiency. And in terms of pipe design, direct pipe design is the most efficient. If you are using PI, you don't need to consider using reverse return anymore, because the idea of the reverse return is that you balance the system without using balancing valve. But in this system, when you use PI valve, it is dynamic or automatically balancing. So you do not need to add any balancing valve. And therefore, the same logic applies. If you don't need balancing valve, you don't need reverse return in your system. So reverse return just adds unnecessary costs and complexity. And now we look at some examples of PI valves. Over here we have the simplest. This is called like a PI flow limiter, and flow limiter means that it will control flow at the maximum or zero. So this is very good for FCUs, because normally FCUs will use this type of control, on-off control. And if you can afford a better valve, then this is modulating PI valve, and they are for FCU. And when you have modulating control, obviously the room temperature will be more stable, and your delta T is also higher. So when your delta T is higher, it means that your average delta T is higher. It means that your average water flow will be lower, and therefore you'll be saving energy at the plant, especially at the pump. And over here we have modulating valves for ASHRAE, but this type is a different, based on different technology. As you can see, the appearance is totally different. So this uses a flow sensor and a modulating valve. I will explain further on this in my next slides. Now we look at how the mechanical valve function. So the heart or the key of this valve is actually here. This is the pressure regulator. What the pressure regulator does is that it fixes the differential pressure across the control valve to be constant. When the pressure is constant, no matter what pressure is being applied to the valve, it means that the flow will be constant. All right. So if you don't change the position of the valve and the pressure is constant, therefore the flow will be constant, even though the pressure here is changing. So this is the heart of the system of this PI valve. And as you can see here, there are actually two valves in one. And therefore, mechanical PI valve does have some drawbacks, which is it will require this minimum operating pressure or minimum differential pressure to operate. So if you don't supply that minimum differential pressure across the valve, which you can measure with this PT test port during commissioning, it doesn't function as a PI valve. So you have to supply that minimum differential pressure. And another drawback of this pressure regulator is that it's mechanical, so it's prone to wear and tear, and it's also prone to clogging. But there are some better designs, like as you can see here, the flow passages are bigger. So this is designed to be operated in situations where the water is not as ideal. And this is the commissioning process where you use digital differential pressure meter. So as long as you have 16 kPa, it is in PI mode, but not more than 350. If it's more than 350, it is also not able to control the flow. And as an example here, it's reading 200, so it's actually too high. You can actually reduce the pump speed. If this was at the index branch, you can actually reduce the pump speed. And how you reduce the pump speed is by setting the differential pressure control lower, and therefore you have a lower DP here, and therefore you save energy at the pump. And here is a typical installation schematic. So, and showing the accessories that's needed in the system. And for most of the mechanical valve, you would need a bypass here. That's to protect the sensitive pressure regulator from debris or dirt in the water during T&C. And if you have hundreds of PI valve, that's actually very time consuming and takes a lot of resources. But there are some designs where you don't need this bypass valve, because they have taken into consideration that, you know, the pressure regulator has to withstand some of this debris or the chill water that's not that ideal. So depending on the design, some of them may not necessitate having this bypass there. And next we come to electronic PI valve. Another name of PI is actually called flow control. So as the name suggests, flow control means that it controls the flow without the influence of or isolating the influence of pressure change in the system. And to control the flow, we need to measure the flow. And this device is conceptually is the simplest there is. You measure the flow, and therefore you control the flow with one modulating valve. The advantages are many to this design, but the more important ones are you get a very low minimum delta P requirement. That's because you don't have a mechanical pressure regulator here anymore. You only have this one modulating valve. And this is ultrasonic flow sensor, and there are no mechanical parts here, so the pressure drop is very low. And when the pressure drop is low, it means that your pump head is lower, and therefore you get to save energy there. And because of this flow sensor, you get real-time flow reading. So this is very important if you need to monitor your system. And also for retro commissioning, this makes the work much easier, because you like pump optimization, you can see the actual flow, so you can adjust the differential pressure or the pump speed very easily with this setup. So super quick testing, commissioning, and pump optimization with this control valve, especially if you connect it to the building management system, which most of this device would come with built. And this is the illustration showing you the difference between mechanical valve and electronic valve in terms of pressure and flow. This is a mechanical setup, and it requires this minimum differential pressure regardless of what flow it is controlling at. And this is typically starting at about 35 kPa or 0.35 bar. And this goes up if your valve is bigger. If your flow is bigger, you need a bigger valve, and the minimum differential pressure goes up. But it's different for the electronic valve because it doesn't have this regulator. And as you can see here, the differential pressure is much lower than this 35 kPa for most of the time, like say 90% of the time at part flow. And like over here, I like to illustrate to you what it means by pump optimization. So as you can see here, if I apply a higher pressure across the valve, this is the valve position, and therefore the pressure drop is higher. But as I reduce the pressure that's applied to the valve would normally not automatically adjust itself to second opening position, and the pressure drop is lower. So you can optimize the pump by reducing the speed, and then also observing the flow through the valve, and you adjust the speed, the maximum speed of the pump, so that it doesn't provide excessive pressure to the valve. Okay. And to set up the EPIV, it's very simple. You can use a tool like this to set the maximum flow and also to read the actual flow. And you can also link it to a laptop and log all the data for analysis later. This would be a typical installation. And you can see here, you don't even need a strainer, because you only probably need a strainer for the entire system, not for every coil or every valve. And here is I like to emphasize what the difference between position control or the traditional valve and a PI or flow control. And over here, a traditional valve doesn't know what is flowing through the valve, so it just functions to provide the position. So this is the control signal, and the position of the valve would change linearly. But for a control valve to control flow, control the capacity of the coil properly, we need to set it up so that the flow increases in this way. We call equal percentage. And the reason is because of this inherent characteristic of the coil. With equal percentage flow, we balance out this characteristic, and what we get is a linear response to the power output. All right, but this is this may be different if the pressure across the valve is different, because if the pressure changes, or let's say increases, then the flow would increase and it will have impact on the actual power that's coming out from the coil. And of course, it's dependent on the coil characteristic and also the supply chill water temperature or the air temperature that's entering the coil. So these are the things that we don't know, and this will influence the control. And that's why using traditional valve, the system is not as stable, and you need to check. Okay, so if let's say it's not functioning properly, you need to install some instruments on it, like a flow sensor, or to measure the water temperature, the air temperatures, to check out what's happening at the ASHRAE. But if you were to use a PI valve, then it takes one important element of the equation now, which is the pressure, which influences the flow in the system. So you get this equal percentage flow control all the time accurately to plus minus 5% or whatever that's in the specification for the PI valve. And the result is this linear response, but it's still under the influence of coil characteristic and temperature. And now, what if we integrate the thermal energy meter and a PI valve together? And this is what you will get. And we can name it like energy valve, which means that it is a valve and also it's thermal energy meter, 2-in-1. And we can, with more sensors in this integrated device, we can also realize a smarter device. So a smart device means that it can adapt to the situation as the situation changes, without you having to manually interfere. So this smart PI valve can also learn and optimize automatically because it has these sensors that's taking in reading and data. So for example, is that it can increase the average delta T in reducing the flow, okay, depending on the situation, that's how the ASHRAE is running, and then saving you significant energy at the plant and especially at the variable speed pump. Installation wise, just like any other control valve, but now you need to install temperature sensors to measure the delta T, the supply chill water temperature, and the delta T is the difference between the supply chill water temperature and the return temperature. And if it's connected to the cloud, all this data not just reside in the device or at the BMS, it can be uploaded to the cloud where it can help with monitoring and managing this device. And you can have, for example, these extra services that can help you to optimize your building, like automatic optimization of delta T and flow settings, performance report that's available to you for analysis. Okay, so and you can access this data anytime, anywhere, because it's residing in the cloud. And the efficiency of the product is ensured because it can get software updates pushed to it. This would be an example of how the such an integrated device would look like. You will have the modulating valve to control the flow. And then this is the energy meter part where it consists of two modules. You have the logic module here and also the interface and the powering. And over here is the sensor module, which can be removed for calibration. And examples of such a device would have these features here where you can control and also build the energy, thermal energy that's been used. And communication wise, example like here, it's power over Ethernet. It means that you can power, you can communicate, you can control from just one LAN cable, like a Cat5 cable. And it's an Internet of Things device where the data is pushed to the cloud, and the user would be able to learn how much energy is being used by just accessing an app in his phone. And it would have all these communication protocols built in, so it makes integration into the BMS very easy. And also using the phone app, you can commission the product, which means that all the reports are easily available in the cloud and accessible anywhere. And using the right flow sensor, you can also have it to compensate for different varying glycol concentrations in the chill water. So ensuring that you get accurate reading of the thermal energy. And with the integration of this energy meter into a valve, we can have this type of control where we call power control, because the energy meter is able to tell you in real time the actual power of that coil or the ASHRAE. And therefore now, if you know the actual power, and this is what we want to do to have linear power response originally, but as you can see here, we weren't able to do it effectively because it's under the influence of these factors here. But now, knowing exactly the power, we can control the power accurately. And the advantages are it's independent of all these characteristics, factors that's affecting accurate control. So therefore you get constant power, and it also responds faster to changes in the supply chill water temperature, which often does. Okay, so when we say let's say we design supply chill water temperature at 7 degrees C, it's not always at 7 degrees C, so it can be higher sometimes. And if your chill water plant has this protocol where you want to increase the chiller efficiency by raising the supply chill water temperature, and you can do this for day and night times as well, because as you can see here, this valve with power control will automatically manage the power of the coil much more effectively than if it's a PI valve or flow control valve. And which brings I forgot to mention that with power control, you can have a very stable supply air temperature for which you require for a VAV type setup of ASHRAE. So that power control is really suitable for that. And which brings us to VAV. So now we look at what are the components that's found in the VAV. And VAV stands for variable air volume. And what it does is that it changes the amount or manages the amount of air into a particular zone according to the cooling load that's required. So higher cooling load, more primary air or supply air into that zone. Very simple logic or control. And how it does that is that first it needs to measure the airflow that's going through. And over here, it can be a orifice plate or can be a cross. Okay, so some people call it a cross, some people call it a differential pressure averaging sensor grid. Okay, that's a long name, but that's the technical name for that. And what it does is that we measure the differential pressure here, and you would get you would translate that into flow in this controller. And this controller would compare what's measured and what's required. Okay, so what's required comes from the temperature controller. So this will be the flow set point from the temperature controller. And this is located in the room normally. And comparing that, you get an output to the actuator. And this actuator will modulate the damper to get the correct flow that's required by this flow set point. And now I think you will realize that this setup is somewhat similar to what I've explained earlier about the electronic PI valve for chill water system. So we can actually draw some parallels between them. And the mathematics behind converting pressure into flow is this. So we can simplify this equation. Okay, so because the rho value or the medium density, the air density doesn't change. If let's say for same building, okay, so we can simplify the equation to become like this. And this is also somewhat similar to the equation that you will use for valve selection. Okay, V equals to KVS multiply square root delta P over 100. Okay, so it's similar because this is regarding fluid control. And this C value here, it's normally not provided in the VAV data sheets. So if you need to find out this one, you have to ask the manufacturers for it. And this is important because this value calibrates, is needed for the calibration of the VAV box. And this is how it would look like. You have this sensor grid here. So this is called a center averaging grid because the pickup is from the center. They have different manufacturers would have different design, but they would have a relatively similar performance. So this pickup and the differential pressure goes to this compact unit. So controller, actuator built in, okay, into one, and this will modulate the damper. Now we look at VAV system, okay. So It consists of this ASHRAE over here and the VAV boxes. So we have explained or discussed how this works here, and now how the ASHRAE works. So we will have a differential pressure sensor here to maintain sufficient pressure in the duct system so that the VAVs here are able to work properly. Just like the PI valves, you need sufficient differential pressure so that it works properly. So in this case, the same thing. So we maintain sufficient pressure here. And this is a variable speed fan. And the idea behind the VAV is that when the load is low, the airflow is low, and therefore you save energy at the fan. Okay, so similarly for chill water system, when the load is low, you need a lower chill water flow, therefore you save energy at the pump. And then here you will have the control valve. So the PI valves will be located here, controlling the coil. And this valve's function is to maintain that this supply air temperature is constant. And normally we set this to around 12, 13, or 14. Okay. And then over here, typical VAV ASHRAE setup, you have filters and then mixing the return air, and this is the outdoor air coming in through here. So VAV and CAV, they are a different thing, but a lot of people would think that they still serve the same function, which is to maintain the air temperature here the same, and then they would have similar performance. But actually, VAV system is much more superior if you to compare to a CAV system. First of all, is of course the energy saving that you get from reducing the fan speed. Okay. The second is that here, if you look at the psychrometric for both, the orange is VAV and black is VAV, orange is CAV. You find that the humidity is much better with a VAV system. So over here, you look at this RA or return air. You see that the humidity for VAV is at 57%, but for the CAV is at 67%, much higher, and it's near. Normally in Southeast Asia, you want to control it below 70. Otherwise, there will be more, and this is already very near that. So, and that's why you find that the humidity in most hospitals or shopping malls or offices is not able to control at what you want at part load, because it is the inherent property of a CAV system. It's just not able to control humidity that well. But if you were to design with a VAV system, that problem is totally eliminated, as you can see here. So the reason is because for a VAV system, we always maintain the supply air temperature at a constant design level. Let's assume this is 12 degrees C, so it's always there, and it's always removing moisture, no matter what the load of the ASHRAE is. But for a CAV system, as the load decreases, as the valve modulates flow, the supply air temperature becomes higher, and it's not effective in removing moisture anymore. All right. So even though the dry bulb is the same in the room, but the moisture level are different because of how the coils are controlled. And these are tabulated results showing the same thing. Like here at part load, it's 60%. At peak load, is 57%. So the RH is rather stable if compared to a CAV system, which fluctuates. And as you can see, it's already out of the 70%. And to optimize the energy use, we can use a method where we monitor the damper position. So this first slide here shows you using pressure to control. Okay. And this is at peak now, and this damper would need to be at 90% to modulate the flow, whereas the other two is 100%. But let's say we are at part load, then these dampers would need to be at 50, 20, and 20. And that's because the duct pressure is maintained still high using this control method here, using pressure sensor. So this wastes energy at the fan, even though we are saving flow, but we are not saving in terms of reducing pressure. So we can do that by monitoring the damper positions. And what the controller in this example would do is, or the optimizer we can call it, is doing is that it will try to maintain one of the VAV, or if some of the VAV, at 100% open if it can. All right. So when it does that, it will reduce the fan speed, but also trying to maintain the dampers as open as possible. So when one of these VAV cannot reach the airflow, then the fan speed would need to increase. So as we reduce the fan speed, you can see here the damper positions increase, and then the fan speed decreases. So similarly, you can apply such a system for your chill water system. So you can like call it a pump optimizer instead of a fan optimizer. And this would be a typical setup of VAV type ASHRAE in Southeast Asia. So in this example, I've put in as many sensors as is realistic. So to have to monitor as many points as possible to ensure an efficient ASHRAE. Example will be this duct pressure, and this pressure and flow pickup to monitor the flow. And for the outdoor air, you might want to monitor the flow as well, because the outdoor air is expensive to condition. And you will have various modulating dampers here to control the outdoor air and the return air. Okay, so sorry, this is the return air here. Sorry, outdoor air here, and this is the return air. And over here will be the mixed air, and you will have temperature, humidity sensors located at all the 3 branches. And for the filter, you can have this differential pressure sensor, or you can have differential pressure switches. And now, with this much actuators and sensors, it would be rather complicated to use analog system to wire them back to a controller. So as you can see here, the wiring is rather complicated, and it could be prone to mistakes as well. And we can fix this easily, or if you are using BACnet or smart devices. So now all the actuators and the sensors or the drives are connected using just one pair of BACnet wires. And besides very easy to wire them up, you also get more accurate data, because these are digital, it's not analog signals. And you don't get errors as well, because you're using BACnet objects instead of using conversion or scaling.
I think the time is almost, I think it already end. Can you make it faster on this one?
Yeah.
Go ahead.
Okay. Yeah, so I'd like to share with you here some options where you can wire up the sensors. So these are conventional analog sensors, passive and active. And now you have BACnet sensors, and you can also have sensors where it's integrated to the actuator and then connected to BACnet or the BMS. So because the reason is because the actuators and the sensors normally come together in a device or equipment. And you can also have the sensors and the actuators connected to the cloud as well. Okay, so since we have run out of time, so I will close my presentation here. So thanks, and back to you, Ardi.
Thank you very much, Alvin. I think the remaining is about the building energy information system. Yeah, you can. I think the material is also allowed to be shared with the participant, right, Alvin? So they can take more benefit out of it.
Yes. Yes.
Okay. Thank you. I think I just there are actually several questions, but what I would like to do, I think I would like to ask the committee to recap the question and then give it to the speaker, and then if they can answer it in writings, we will post to the email of the questions on that. So feel free if you have any more questions. But there's one over here. I try to make it concise first. What's the length of your power meter, the BTUH meter, between actuator and the motor? If you want to put the monitor on different locations, what would be is there any limitation on that? And then second one is the independent flow valve can work precisely, but the sensor took the pressure sensors actually for the flow. So it's a pressure difference on that. That will depends on the VSD or PFD operations, and also the fluctuation of the load. Not only the indoor temperatures. Can you give any opinion with this assumptions?
Yeah,
Thank you.
I'll answer the first question regarding the thermal energy meter and control. So if you are using a digital protocol like BACnet, then there's no limitation on the distance, so you do not need to worry about that. And on the second question, I'll try to read it again to understand what is trying, what the person trying to ask. Okay. Well, I'll try my best to answer this one because it's rather long, and I'm not 100% clear of the intent of the question.
I think they asked how accurate your flow sensor is.
Yeah, the accuracy of the flow sensor is 2%, and in terms of control is 5%.
5%.
So, yeah, meaning if you ask it to provide 1 liter per second, then it will be plus minus 5% of that 1 liter per second. And it is pressure independent. It means that whatever pressure change in the system, it will maintain that flow as long as you don't change the set point. And if you use an integrated device with energy meter plus the PI valve, you can maintain the power plus minus 5%. And this is even better because even if the chill water temperature change, the power of the coil remains 5%. So that's even better. Yeah.
Okay.
So, okay.
Thank you, Alvin. I hope they can utilize the feature that your products have in this case. Thank you very much. Since we have a limited time, I would like to have closing statement from you, Mr. Alvin Chan, regarding I think the whole sessions this morning with you and Jim. Do you have any closing statement? And then after that, I will ask Jim to come back again and then give his closing statement. Probably 2 to 3 sentences that can be a takeaway from our session the whole morning.
Yeah, yeah, I'm very glad that you know, all of us are looking at the same thing or thinking the same thing in terms of IAQ or building energy efficiency, and that's good because we need to work on this as one, you know, not having different parties doing different things. Yeah, yeah, that's my conclusion of.
I agree with that, Alvin. We have to act as one solid team on this case. Jim, could you please give us like 2-3 sentence takeaway from the whole morning sessions? Sure. Go ahead, Jim.
I think this was terrific. I saw how many people you had on there, and they all stayed on pretty much to the end. That was very impressive. But Alvin, I want to tell you that was a good presentation, and I did mention they were going to get some information from Valimo later on, and you gave them good information. So this was a real pleasure. I had some good questions. I was very impressed. And now I have a better feel for what your average temperature is too. You don't have to worry about it being 0 or 5C.
We won't get there. Go ahead. Do you have any closing statement for the participant to take away with?
Well, I did make a note that I was going to break down that air cleaning technology chart so that everybody can really get the parts of it and put it together. So I'll send the full one and then about five separate PowerPoints that'll give everybody what they need to see. And I hope that people got a lot out of it. It's always difficult when you're doing something for a country that's very different and totally different temperatures and humidities. I had to rethink some things real fast. but I had a good time.
Yeah, I think we learned a lot today, and then hope also you can learn something or take away something from our discussion this morning. Yeah.
I'm wondering, do you know if any of your people are coming to Toronto for the meeting the end of June?
Well, let us the participant. I usually come to the winter conference, but this one is in Toronto, so it's pretty far. I heard that Region 13 chapter presidents and committee chairs, the Region 13 will come, like Apichit will come, and then not sure from Indonesia. Probably I have to ask. Maybe usually Pak Dedi also sometimes comes there. But this is really that is far away from Indonesia.
Sure it is. It's just very far away from Indonesia.
Okay. Unfortunately, we have limited time. I would like to thank you, Jim. Thank you, Alvin, for your sharing today. And then would like also to thank the ASHRAE Indonesia Chapter, of course, Pak Asep as the CCTC chair, who make this session possible. For our sponsor Belimo, thank you very much for the support, and also for all the participants. Untuk Bapak dan Ibu yang hadir hari ini, terima kasih sekali. Semoga bermanfaat untuk kita semua. Ini seharusnya ada closing remarks by ASHRAE Indonesia Chapter President Pak Fatur Rahman Yudi, tapi beliau sudah mengamanahkan ke saya untuk memberikan penutup. Tapi pada intinya adalah ASHRAE Indonesia selalu ingin meningkatkan profesionalitas kita ya di Indonesia dalam bidang HPACR, dan ini adalah salah satu kontribusi di sana. Kita juga memiliki beberapa kegiatan lain yang mudah-mudahan bisa meningkatkan profesionalitas dari anggota-anggota ASHRAE. Jadi ya, mewakili ASHRAE Indonesia, kami ingin mengajak untuk Ibu Bapak untuk terus meningkatkan kompetensinya, terus meningkatkan profesionalitasnya dengan melalui penerapan standar maupun pedoman yang sudah dibuat oleh ASHRAE Society yang sudah cukup lama dan dihasilkan dari proses yang cukup kompleks. Tadi disebutkan adanya technical committee, di situ dibahas mengenai standar maupun pedoman tersebut. Kami menyambut baik usaha-usaha dari pemerintah maupun asosiasi lainnya yang mempunyai misi yang sama, yaitu meningkatkan profesionalitas dari engineer maupun arsitek maupun profesional di bidang HPACR. Mungkin itu dari saya. Terima kasih sekali, dan saya mohon maaf kalau ada kesalahan atau kekurangan. Terima kasih. Saya tutup. Saya kembalikan ke host kita, Ibu Wira. Terima kasih dari saya. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Bu Wira, silakan saya kembalikan.
Baik, terima kasih Pak Ardiansyah, ya tim yang sudah memimpin panel diskusi kita pada hari ini, dan kami juga menyampaikan terima kasih sekali lagi kepada Mr. Jim Newman dan Mr. Alvin Chan yang sudah menjadi narasumber kita pada hari ini. Dan kami dari ASHRAE Indonesia Chapter yakin bahwa materi-materi yang diberikan bisa bermanfaat dan berkontribusi bagi industri gedung dan bangunan di Indonesia. Sebelum berpisah, saya ingatkan sekali lagi, bagi rekan-rekan semua yang ingin bergabung menjadi member ASHRAE atau ingin mengetahui lebih lanjut mengenai apa itu ASHRAE Indonesia Chapter, bisa langsung mengunjungi website kami atau menghubungi nomor WhatsApp yang ada di kolom chat. Di sini ya, di kolom chat kita. Demikian rekan-rekan sekalian, kita sudah sampai di akhir acara. Sekali lagi saya mengucapkan terima kasih atas support dan partisipasi rekan-rekan semua di acara hari ini. Kami mohon maaf jika ada kekurangan atau ada hal yang kurang berkenan terjadi selama webinar ini berlangsung. Akhir kata, kami mendoakan supaya kita semua sehat dan fit, sehingga kita bisa bertemu kembali di acara ASHRAE Indonesia Chapter berikutnya. Sekian, sampai jumpa lagi. Terima kasih.
Thank you. Bye-bye.
Thank you, Jim.
Bye. Thank you.
Thanks, Arvi.
Oke ya, terima kasih ya, Bu Wira, makasih ya Bu.
Sama-sama Pak, terima kasih semuanya.
Pak Ferdian
Well done,
juga makasih,
sukses.
Pak. Adminnya
Makasih,
juga
Pak
makasih nih, banyak bantu. Ya kita ketemu lagi
Ferdian.
mungkin April atau Juni ya, mudah-mudahan bisa offline.
Baik Pak,
Siap.
terima kasih. Sampai
Ya,
ketemu, Pak.
saya langsung ini ya turun ya.
Oke Pak Asep.
Ya, selamat
Sukses,
siang
Pak Asep.
semuanya
Thank
ya.
you.
Bu Wira.
Pak Ferdian semuanya, bye. Thank you.